Hey everyone, this is Mr. Kerr. This video we're going to be looking at Newton's third law. So I thought I'd start by looking at this soccer player here. And the soccer player is kicking the ball, and this is a great example of Newton's third law because Newton's third law is all about objects interacting with each other. That's what happens in the real world. So if you push or exert a force on something, you're going to feel a reaction force associated with that interaction. So let's draw a little free body diagram here to show the forces. So I've got a ball, and the ball here is going to be kicked by the player. So I'm going to label this force over here F player on ball. This is my action force. I'm just going to label, but it's more appropriately labeled F player on ball. Now remember what happens according to third law, the other object, the player, is going to feel the exact same force but in the opposite direction. So we're going to have F ball on player. And this is my reaction force on this side. So you feel the same force, both objects. Opposite direction though. Now what's going on though is the motion's not necessarily going to be the same. We know that the ball is going to be accelerating a lot more than the player. Why? One word, mass. Mass is the big difference here. So let's look at an example. What I have here, I've got a cannon. It's firing a cannonball. Now you can see the cannon slowly moving backwards. It's a slow motion. But you can't even see the cannonball. It's accelerating tremendously. So the cannonball has an incredibly large acceleration. And what's going on with the cannon, it's much, much smaller acceleration. Why? Again, mass. Much larger mass, much, much smaller mass. So let's look at that on this page here. So again, what's going on is you're going to have the two forces. So you got the cannon on the ball and ball on cannon. And they're exactly the same size. What the difference is again, the mass. Mass determines the acceleration because of second law. So remember, second law states that the acceleration is inversely proportional to the mass. So if you've got a small mass, large acceleration. Large mass, very small acceleration. You can really see it down here as well when you put the two forces side by side and equate them, right? So again, that's kind of the idea of mass. So what we're going to do is we're going to be looking at some examples today in terms of calculating Newton's third law. But I do want to mention that all of these involve these basic ideas of the two forces being exactly the same, but the reaction force is in the opposite direction. And the notion that the acceleration depends on mass. So the motion is not going to be the same on both. So really pay attention to this and maybe put this on your note if you haven't done so already and put some asterisks next to it. Okay, so we're going to go through one of the examples in your textbook. Now, this is tutorial 2 in your section on third law. And I've just modified it slightly. So I've got additional questions I'm asking. And basically the idea is this. You've got two skaters. You've got one skater here. I'm going to draw a little free body diagram. Both of them have, sorry, let me just close this. Both of them have gravity and normal forces acting on them, but we're going to ignore them for now. We don't need them for the time being. In the future, we'll have to do this, but just for now, ignore them. So the major forces are what's happening with the two skaters. Now, the first skater, she's pushing on the second skater here backwards, or sorry, not backwards, but in a direction eastwards. So I'm going to call this F1 on 2, and it's going to be 70 newtons to the east. Let me put this over here. Now, she's going to experience, according to third law, the same force, but in the opposite direction, westward. So we'll label this F2 on 1. So it's the force of player 2 on 1. And it's going to be negative 70 newtons. The exact same size, but in the opposite direction. Now, how about the acceleration? We know the second skater has a larger mass. So because it's a larger mass, the acceleration is going to be smaller. And we're actually going to calculate the acceleration in some other quantities here. So just for the sake of time, I've done some of the work already. So here's my free body diagram for each skater. Okay. You can see here how we've added normal gravity, we're ignoring them, and we've got the horizontal forces. Now, since friction is going to equal 0, the sum of the forces here for the first skater is simply going to be just the F2 on 1, 70 newtons. And on the other side, the sum of the forces is going to be 70 newtons, but forwards, or eastward in this case. And then what we can do is we can use Newton's second law. So remember, the acceleration depends on the net force over the mass. So on each side, we can do the calculation. So 70 over 50 for this first skater. She has a lower mass, and it with an acceleration of 1.4 meters per second squared negative. So she's going westward. And now remember, the other side, he has a larger mass, and because of that, the acceleration is going to be a lot smaller. When you calculate it, it's only 1 meter per second squared. Again, this is because of second law. So what we've done is we've drawn free body diagram, we've done the net force, we've even calculated the acceleration. Now it's time to write down some therefore statements. Okay, so one thing you should do is always be careful with significant digits. So we're going to go back up here and see that we have 3 significant digits in all of my givens here. So as a result, my statements here are going to reflect that. So skater 1 should be skater 1, accelerates at 1.40 meters per second squared to the west. And the other skater accelerates at 1.00 meters per second squared towards the east. Okay, so remember, keep those significant digits there and include the direction. Now we also have to account or explain what's going on. So we know it's second law, but you have to explain why there's a difference between the motions. So write down something like this. This is a good model. So according to second law, the acceleration is inversely proportional to the mass. Therefore, the acceleration of skater 1 is larger than skater 2 due to her smaller mass. And that's it. So basically stating the law, the proportionality, and how it applies in this particular situation. Okay, now the last part we have to do is we have to determine the speed or the velocity of each skater after traveling or after 0.25 seconds. So what we know is this. We're going to make a little bit of an assumption that each skater is motionless at the beginning, and we know the acceleration, and we know it's going to be after 0.25 seconds, and I want to know the velocity. So according to that, we're using this equation. We're just going to simply rearrange it. So we're solving for v2, and we're going to substitute our values in here. So they're basically exactly the same. The only difference is going to be the acceleration. Remember, the acceleration of skater 1 is a lot smaller. And when you actually do the calculation, you'll find that the first skater has a larger velocity. Well, it makes sense. She has less mass. She can accelerate more with the same amount of force. So at the end of the day, we're going to write down therefore statements. Now, the only thing to be careful with here is the given we're using, 0.25 seconds, only has 2 significant digits. So that means my final answers can only have 2 significant digits here. So the velocity for skater 1 is 0.35 meters per second to the west, and skater 2 is 0.25 meters per second to the east. All right, in this next example now, what's going to happen is we have a little bit of a different situation. Still like third law, but we're going to have friction now. That's a big difference. And I'm going to start with motion and then go into the forces afterwards. So we've got the stationary toy tank. It's shooting a plastic projectile that's also stationary. Note the units are kilogram or grams. So we have to convert these to kilograms later on. So that's something to kind of keep in mind. We know the projectiles accelerate from rest to 3.5 meters per second, and it's accelerated over this little barrel here, and it's 15 centimeter length. So again, we have to change this to meters, and we'll have to determine from that motion. Looks like we're going to have to figure out our acceleration. So here's what we have. We have our motion. We're going to know the initial velocity. We're going to know the displacement. It's going to be 0.15 meters. Just going to do a couple quick givens here. And I need to figure out the acceleration. So I also have my final velocity, and I'm trying to figure out my acceleration. So we're going to be using a motion equation. And then from that motion equation, we're going to get our acceleration. Once I have the acceleration, we can figure out our overall force. Now, we are given information for the projectile, so keep that in mind, okay? Some students mix up the motion and use this motion with the tank. No, this is for the projectile. So you're going to figure out the force on the projectile. And then once you have that, we're going to determine the action force on the projectile. In other words, the toy on the projectile. And then from third law, we're going to figure out the reaction force, the projectile on the toy tank. Okay, so that's kind of like an overview of what's going to be happening here. So let's look at the actual values. So first thing we're going to do is we're going to draw free body diagrams for each, always, okay? And we're going to make a conversion for the mass. We know we're going to be using it. So the thing here is we're going to have force of friction on the projectile. So really add that in. Make sure you add that into your question. So we're going to have the action force on the projectile, which is the toy on projectile. We're also going to have the force of friction. We're going to assume it's 0.50 newtons, and we're going to assume it's going backwards. So over here, we're going to have a little compass. Up and forward is going to be positive. And I draw the same thing for the tank. We don't know any information about the tank in terms of friction. That's okay, we'll leave that for now. But we do know that the reaction force is going to be equal to the action force, just in the opposite direction. So, as I said earlier, we know all the motion, but it's the motion for the projectile. Do you notice how I set up this question? So I've got the tank information on one side, projectile on the other side. This prevents me from using the wrong values for the wrong object. Okay, so once we get the acceleration, we substitute it in here, and I'm going to find it's going to be 40.8 meters per second squared. So that's the acceleration of the projectile. Then we can determine from that the overall force, the net force. And here it's going to be 2.04 newtons forward. So I can actually add this up here if I wanted to. Or sorry, we don't know, because the sum of the forces is going to be 2.04 newtons going forward. There we go. Now, what's going to happen is I have to figure out what is the actual action force. This is where this question is different from the other questions, right? So let's look at it. So when you look at the statement here, the sum of the forces is equal to the action force, tank on the projectile, plus the force of friction. You really have to be careful with this. So I know the overall force is going to be 2.04. The tank on projectile, that's going to be the action force. I'm trying to solve for that, and I know that a friction force is going to be backwards. It's going to be 0.50 newtons backwards. So when you solve, you're going to end up with 2.54 newtons. That's your actual action force. So some of this force went towards accelerating, and some of the force went towards the force of friction here. Okay, that's why it's a little bit larger. Then, now that I know that, so I know my overall force acting, or the action force acting on here, 2.54 newtons, I can say, hey, I know that the reaction force, the projectile on the tank, has to be exactly the same, but in the opposite direction, right? We know that. So down here, you have to have a little statement saying that in your answer. So according to third law, the force of the projectile on the tank, the reaction force, is equal to the same as the tank on the projectile, the action force, but opposite direction. That's exactly what we have up here. And then you have a little therefore statement at the end. Remember, the question was asking us up here, determine the magnitude, the size and direction of the action-reaction forces. So, little therefore statement with two significant digits. The action force is the tank on the projectile of 2.5 newtons forward, and the reaction force is the projectile acting on the tank, 2.5 newtons backwards. So that's it. So again, keep this in mind. This is the key difference in terms of the steps. Just this one little bit here whenever you're dealing with friction in these types of problems. So that's it. You have some practice examples to work on, and that's about it. Hopefully you enjoyed this video. Bye.